Okay, we are recording. This is 13.5/6, Pendulums and Simple Harmonic Oscillators. Pendulums are simple harmonic as long as they're under 13 degrees. They conserve energy. The lowest part of the swing is all kinetic energy, so it's moving its fastest. The top part of the swing is all potential energy. It is not moving. It hits a velocity of 0, and it's max height. And there was something else in there, but I can't remember. Anyways, so here's the equation for the period of the pendulum. The period, capital T, equals 2 pi square root of L over G. This is very similar to that of a spring, which is 2 pi the square root of M over K. Your period is measured in seconds. It's the amount of time it takes for one cycle. Let me write this down. Remember, period is seconds a cycle, and frequency is cycles a second, which is equal to hertz. The period for a pendulum, 2 pi square root of L over G. Period for a spring, 2 pi square root of M over K. See all blue cups, so we should be good to go. Here is a picture of a simple pendulum. You can see the equilibrium straight down here. The restoring force is the mg sine theta part, where its current angle is at this. And then you can see straight down is going to be your mg cosine theta. So this one is not affecting, this one is perpendicular to it. So this one doesn't have an effect on it, but this one is the one that's the restoring force. So as it gets closer to this point, this angle becomes less and less and less, making this go to 0 and this increase. So until your restoring force becomes 0. So that's why it's maximum velocity. So instead of force like a spring, force equals kx. Well, here for a pendulum, force is equal to mg sine theta.
What is that T?
That is tension of the spring.
No, I meant in the equation. Next to the
this one?
Yeah, the subscript.
Force of that.
Yeah, they're talking about the restoring force for the pendulum. I don't know what that is. I don't think it's a T. I'm going to go with they mean pendulum. So
Okay.
the restoring force for a pendulum.
Okay.
I wouldn't call it FT.
Okay.
Actually, I'll write that up here on the board too. So the restoring force for a pendulum is going to be mg sine theta, and the restoring force for a spring is negative kx. Where this is just saying the opposite direction in which it was pulled, and this one is going to be the opposite direction, from which its angle is. So the angle should take care of it.
Also the force behind the pendulum when it swings?
It's restoring force, but this is the restoring force for a pendulum, and this one's for a spring. And you can't set them equal to each other because one's for a spring, one's for a pendulum. Energy and pendulums. The potential energy for a pendulum is going to be its height and its gravitational pull. So at its highest point, you're going to have the potential energy where H is max. So that's where the H max comes in. And then any other point that isn't the very bottom is going to be some potential with that height in it plus some kinetic. And then where it's equal to its maximum velocity, you could go equals over here to 1/2 mv squared max. This is all kinetic, so it goes kinetic to this one. But if you catch it somewhere in between, this is its max energy, its total energy. So all the energies have to both add up to that maximum energy. Let's draw a picture. Pictures. Now, this is a very common type problem in the AP pre-response questions. They'll give you some sort of angle. Sometimes it's a tricky angle, like they'll give you this angle that they really hate. They give it to you. And they'll give you the length of the string. So you know that down here, at this part, it's the same length. I know that doesn't look like it. Just pretend it is. So it swings down and it swings back up. So at this point, it has all potential energy. And here it has all kinetic energy. The problem is you need the height for this potential energy. So H, not L. It's kind of tricky, isn't it? So that is very common. That kind of problem is going to show up on your homework. It's not very fun, but using trig, you should be able to solve for it. And basically what you're going to find is H here, and L minus H to give you, you'll find X up here. This is X. Just messed up my pen. This is X. So you use a trig function, which would be opposite over hypotenuse, which is sine. So sine theta gives you X over L. Solve for X, so you'll have X as L sine theta. And then to find H, you know that X plus H equals L. You guys see that? This is X. And then we know this potential is height. So both of them should add up to equal L. I would definitely write this down. You're gonna have one of these. Once you know H, so you can solve for H, you can plug it into this energy, potential energy equaling kinetic energy. And a lot of times it'll ask you, it'll give you the setup, and it'll say how fast is it going at the bottom of the swing. So once you do that, you just do mgh 1/2 mv squared. And you'll see your m's cancel out, so they probably won't even give you a mass.
Okay, so mgh is what's PE?
The potential energy, gravitational potential energy. Mm-hmm. Yeah, for a spring, it's specific. Like a spring has an equation for potential energy. But since a pendulum only works on gravity, it's just the gravitational potential energy.
Okay, good.
Can I move the slide at least? Okay. Pendulums and accelerated frames. Many questions that you're going to come across that have that ask for like different periods of the pendulum. You're just looking at like compared to the Earth. So instead of G for the Earth, like 9.8, you're going to use that for the Moon, 1.6. They get a little bit more complicated when you talk about pendulums in an elevator. So just think about whether you're getting heavier or lighter, and you either add or subtract G. If you think you're getting heavier, like if you're in the elevator and the elevator starts to accelerate upwards, then you're going to get heavier. So if you're getting heavier, you're going to add to G. 9.8 plus whatever your elevator is accelerating. Let's say it's 4. So it would be 13.8. If you're in an elevator and it's accelerating downwards, for instance, like dropping out from underneath you, you're going to feel lighter. So you're actually going to subtract. So if it dropped at 4 meters per second squared, then you would take 9.8 and subtract 4 and replace the G with that. So try to approach it more conceptually. You can do a free body diagram, net force equals ma, and then find the total acceleration from that and plug your acceleration into here. But that's a lot harder than just adding or subtracting. So think about it conceptually. Are you going to get heavier or are you going to get lighter when this happens? And then plug that number in for D. All right, now we're going to talk about oscillators. We have damped oscillators. A damped oscillator is undergoing harmonic motion where the amplitude is changing. So, here is a damped oscillator. This is not a damped oscillator. You see why this is not an oscillator and this one is? Mm-hmm. This one's an oscillator because it has a restoring force. It's always going around the center. Whereas this one, it is some sort of wave, some sort of periodic motion. But it's not a simple harmonic oscillator because it doesn't have that restoring force. It doesn't have an equilibrium. So this one, not going to work. This one, good. A damped oscillator, this is kind of a picture of a damped oscillator. You can see that the amplitude is decreasing or is changing. It could be getting bigger instead of smaller. Yes?
Looking at the slide, what's the difference between under and over damped?
Well, I'm going to show you. There's a picture. The next slide has a graph, and that makes it so much clearer. So looking at these, under damped, the amplitude is getting smaller each time it passes through the equilibrium. That's this one, under damped. Critically damped, the oscillator moves towards the equilibrium point and stops once it reaches the equilibrium point. To give you an idea of what that would look like, here is this. It would be slowed down just enough so that it stops at equilibrium. So normally it look like this. Well, then something hits it and it comes down and it comes to rest. That's what we call critically damped. And then over damped is when the oscillator, it releases, it heads towards, but it never actually makes it to the end. So that's like, it's doing its normal pendulum thing. It comes back and then gets over damped and comes out and just holds right here, like it stops. That one. So it never reaches it all the way back.
That makes sense.
All right, so here's some graphs of some damped oscillators. This is also in your book if you want to look at it later. This one's under damped, the blue one, and you can see that it is every time the amplitude gets a little smaller. B shows something that's critically damped. So it comes down, and before it starts to slow down, and this one should actually go and pretty much follow the equilibrium. And then C is over damped. It never reaches the equilibrium. It pauses. It's like holding its position out here. So critically damped is kind of like just enough so that it can stop the motion. Yes.
So, will a underdamped oscillator ever approach equilibrium? Or?
An underdamped one, eventually it's going to lose enough energy that it will, but yes.
It will stop.
Yeah, it should stop. Well, I mean, it's like the half-life of something, right?
Okay.
It never actually ever becomes zero, but it does.
Okay, that's what I thought.
Yeah. And, this is losing energy. There's energy coming out of it. So, eventually it's going to lose so much energy that it doesn't have anything left. All right, how do you guys feel about that PowerPoint? Is it okay? Good so far? Anything you want me to change or add to? Are these better so far? Is it better?